From the moment we take our first steps, we are bound to an unseen force. This force is with us every moment of our lives, guiding our movements and shaping our experiences. It is a silent companion, ever present yet often unnoticed. It tethers us to the earth, dictating our every move, whether we are climbing a hill, strolling through a bustling city, or simply standing still. This force is at work, ensuring we remain grounded. This force, gravity, is a constant companion, yet its true nature remained a mystery for millennia. The stars in the night sky, the falling of objects, and the very act of standing on the ground all point to its influence. But for centuries, humanity could only wonder about its origins and workings. Ancient philosophers pondered its existence, observing how objects fell to the ground, but a true understanding of this fundamental force eluded them. They wrote treatises and debated theories, yet the essence of gravity remained just out of reach, a tantalizing enigma. It wasn't until the brilliance of Sir Isaac Newton that we began to unravel the secrets of gravity's pervasive influence. Newton's genius allowed him to see what others had missed, to connect the dots in a way that would change the world forever. Newton's insights, sparked by the now legendary apple, laid the groundwork for our initial understanding of gravity. The simple act of an apple falling from a tree led to profound revelations about the nature of the universe. His law of universal gravitation provided a mathematical framework to explain this invisible attraction between objects with mass. Newton's equations allowed us to predict the movements of planets and the behavior of objects on Earth with remarkable accuracy. Yet, as with all scientific discoveries, Newton's revelations were not the final word. Science is a journey, not a destination, and each discovery opens the door to new questions and deeper mysteries. Centuries later, another genius would emerge, challenging the very foundations of our understanding of gravity and its intimate connection to the fabric of the cosmos. Albert Einstein's theory of general relativity revolutionized our perception of gravity, revealing it as a curvature of space-time itself, a concept that continues to inspire and challenge scientists to this day. In the late 17th century, Isaac Newton proposed a revolutionary idea, that every object in the universe attracts every other object. This attraction, he posited, is what we call gravity. This invisible force, he argued, is not limited to Earth but extends far beyond, governing the motion of planets around the Sun and the tides that ebb and flow on our shores. Newton's law of universal gravitation provided a mathematical formula to describe this force. It states that the strength of gravity depends on two things: the mass of the objects and the distance between them. The more massive an object, the stronger its gravitational pull. Conversely, the farther apart two objects are, the weaker the gravitational force between them. Newton's law of gravity beautifully explains the motion of celestial bodies. The Sun, being the most massive object in our solar system, exerts a strong gravitational pull on all the planets. This pull is what keeps the planets in orbit around the Sun, preventing them from flying off into the vastness of space. Closer to home, the Moon's orbit around Earth is also governed by gravity. The Moon's gravitational pull is responsible for the tides we experience on Earth. Just as the Moon pulls on the Earth pulls back on the Moon, keeping it in a delicate gravitational dance that has persisted for billions of years. Section 4: Einstein's Revolution, Reimagining Gravity and Space-Time. In this section, we delve into the groundbreaking ideas that reshaped our understanding of the universe. While Newton's law of universal gravitation revolutionized our understanding of the universe, it provided a framework that explained the motion of planets and the force that keeps us grounded on Earth. However, it wasn't the whole story. There were phenomena that Newton's laws couldn't fully explain, such as the precise orbit of Mercury. Enter Albert Einstein in the early 20th century, a physicist with a radical new theory that would challenge the very foundation of how we perceive gravity. His ideas were not just an extension of Newton's work, but a complete reimagining. Einstein, with his relentless curiosity and innovative thinking, developed a theory that would change our understanding of the cosmos forever. Einstein's theory of general relativity, published in 1915, was a monumental leap in theoretical physics. It presented a profoundly different view of gravity, one that was more intricate and elegant than the simple force of attraction proposed by Newton. According to Einstein, gravity was not just a force pulling objects together, it was something far more complex and fascinating. Einstein proposed that gravity is not a force acting at a distance, but rather a curvature in the fabric of space-time caused by the presence of mass and energy. This idea was revolutionary. Imagine space-time as a vast, flexible sheet. When a massive object like the sun is placed on this sheet, it creates a depression. This depression causes other objects to move towards the massive object, not because they're being pulled by a force, but because they are following the curved paths in the warped space-time. A massive object like the sun creates a significant curvature in this sheet, affecting the motion of planets and other celestial bodies. This curvature explains why planets orbit the sun and why objects fall towards Earth. They are simply following the curved paths in the space-time fabric. This curvature of space-time is what we perceive as gravity. Einstein's theory of general relativity not only explained existing phenomena, but also predicted new ones, such as the bending of light around massive objects, which was later confirmed by observations. Section 5, the fabric of reality, visualizing space-time curvature. In this section, we delve into the fascinating concept of space-time curvature, a cornerstone of Einstein's general theory of relativity. To understand Einstein's theory, it's helpful to visualize space-time as a stretched-out sheet. Imagine this sheet as a flexible, grid-like fabric that can be distorted by the presence of mass and energy. If you place a bowling ball in the center of the sheet, it will create a dip. This dip is a simple yet powerful analogy for how massive objects like stars and planets warp the fabric of space-time. This dip represents the curvature of space-time caused by the bowling ball's mass. The heavier the object, the deeper and more pronounced the curvature. Now, if you roll a marble across the sheet, its path will curve as it approaches the bowling ball, eventually spiraling into it. This demonstrates how objects move along curved paths in the presence of a massive body. This is analogous to how planets orbit the sun. The planets are not just being pulled by an invisible force. They are following the curved paths in the space-time fabric created by the sun's mass. The sun's mass warps space-time, creating a gravitational well. This well is a region where the curvature is so pronounced that it dictates the motion of nearby objects. The planets, while appearing to be pulled towards the sun by a force, are actually following the curves in space-time caused by the sun's presence. This elegant dance of celestial bodies is a direct consequence of space-time curvature. Einstein's theory provided a more complete and accurate description of gravity, especially in extreme gravitational fields, such as those found near black holes. In these regions, the curvature of space-time becomes so intense that not even light can escape, leading to the formation of these mysterious and fascinating objects. Furthermore, Einstein's equations predict the existence of gravitational waves, ripples in the fabric of space-time caused by violent cosmic events like the merging of black holes. These waves have been detected, providing yet another confirmation of the profound insights offered by the theory of general relativity. Understanding space-time curvature not only helps us grasp the mechanics of our solar system, but also offers a window into the dynamics of the universe at large. From the orbits of planets to the motion of galaxies, the curvature of space-time is a fundamental aspect of the cosmos. By visualizing space-time curvature, we gain a deeper appreciation of the intricate and beautiful tapestry that is our universe, woven together by the threads of gravity and the fabric of space-time.